the chemical. Oh, thank you for that, Zoom. This research focuses on the chemical and physical processes operating in metamorphic and plutonic crusts. Dr. Dyck strives to develop new approaches to interpreting the rock record. His group studies topics ranging from reaction kinetics and stress distribution during regional tectonics to the bioavailability and geochemical cycling of life essential elements. Their approach integrates thermodynamics, field observation, and analyses of mineral microstructure, crystallography, examining how crustal processes evolve over geological time scales. So without further ado, I'm going to turn the floor over to Brendan, and I would ask everybody to please mute your microphones until the question period opens at the end of the presentation. So thank you, Brendan.
Hey, Fa.
Thank you very much. I am just trying to sort out my screen now.
Hold on a sec here. Let me turn this down. Where's the... Well, thanks, Pop. Yep. I'm just starting to listen to a lecture on the internet for an hour. And then I'll come over.
Would you turn your microphone off, please?
Yep. Okay, bye.
Can everyone see my screen and just a single slide on the screen? Is that what we all see?
You got it.
We see your notes, Brendan.
Oh,
You
okay.
see my notes? Okay.
Yeah.
Okay, thank you. I will
Okay, see you.
I will reshare and we'll try this again. Yes. Okay, can you now just only see my screen? Sorry,
Yeah, only the first slide, yeah.
Perfect. Okay, thank you everyone. Thank you for your patience. Thank you very much for the opportunity to speak today. And in the next 15 minutes or so, I want to talk about a topic that's kind of been near and dear to my heart for the last 5 years, which is understanding one aspect of microstructure. So microstructure is the size, the shape, the way that minerals fit together. And it's that last part, the way that minerals fit together, that has really driven a lot of the research my group has done, whether it be in a metamorphic setting or even in an igneous or an experimental setting. And so I'm going to ask the question, how do crystals self-organize? And I'm going to kind of work towards an answer where we're going to look at how grain boundary energy and the atomic structure of crystalline lattices at a grain boundary, how that influences the interaction between minerals. So I will just hide my own view and in we go. So let's start with a very kind of high level overview. Here we're looking at cross-section through a mineral surface. We have surface atoms at the top, and then that repeats down with our unit cell in our subsurface atoms. Now, along the top, depending on what minerals we're looking at and what atoms we have, we might have a collection of electrostatic forces that alternate periodically. We should expect them to alternate periodically because we're looking at a crystalline surface. And that periodic alteration could be changes in the electrostatic potential. That could be thought of in terms of van der Waals forces. It could be thought of in terms of unbridged oxygen, for example, or just broadly speaking in terms of electrostatic potential. And how components can move across that grain boundary, and how two minerals that have their own surface structure might interact along one of these grain boundaries. There must be some influence from the periodicity of this electrostatic potential. So we can think about this like a landscape of highs and lows, but it's a periodically repeating landscape. And so to explore that idea a little bit, there's a few directions we can go. And I'm going to start with an igneous example, and then we're going to work our way over towards metamorphic and finish with an experimental example that ties these all together. So I'm going to start with this concept of synusis. And synusis, definition of that term is the swimming together of crystals. And this TEM, HRTM image of gold nanoparticles suspended in water really nicely shows what we're looking at here. So if we focus on these two grains that are coming together, this is a repeating GIF here, the two grains that are coming together in the top right, They're starting off as separate. They have their own crystalline structures, the same crystalline structure. And as they approach each other, when they have very similarities in their crystalline orientation, they can meet together, and really rapidly after joining, they develop a neck, right? So they maximize the contact of that, what becomes a very low energy portion of their grain boundary, in comparison to what the free energy would be of the grain boundary that's not touching the same or the other gold nanoparticle. So when we look at it on this scale, we can see, okay, we have these crystalline lattices, and there's this influence from that similarity in crystalline lattice, the orientation of these crystalline lattices as they meet. And the result is that after they come together, they generally form inseparable grains. They're very strongly attached. There's a very rapid microstructural modification right at that grain boundary. And most importantly, we're going to see lattice symmetry across these, what were two initial grains. Now we can think about that lattice symmetry in this kind of word flow here, which is low energy orientation relationships. And we think about this in the sense that any crystals, two crystals that come together, whether or not they're the same mineral phase or not, they will have a lower or a higher potential orientation relationship. Lower or higher energy orientation relationship. And the lowest energy orientation relationship is where we have the most coherency across those two crystalline lattices, right? And so it can be lower when we have the same minerals coming together. It would be higher if we had two different phases, but even in that situation, there's going to be a lower and a higher energy configuration. And why that's really important is because as soon as we get into orientations, it opens up the ability for us to use a technique like electron backscatter diffraction, which allows us to actually image crystal orientations to look for these patterns in nature. So I'm going to show you an example of that, but first I want to just explain how this technique works if you aren't familiar with it. So EBSD is a SEM-based technique where we hold our sample at a very high angle to the primary beam, usually 70 degrees, and then we look at the near surface diffraction or forescattering of electrons. And where they interact with the crystalline lattice, they're either able to pass through or they get blocked by the atoms. And so that develops these Kikuchi patterns that is the array of electrons that then interact with a phosphor screen. They light up, and we just snap a picture of that with a camera. So as we move around, this is an example of steel, so cubic metal. As we move around to different grain locations and we move our beam, we're getting a different pattern. And then the program or the detector in your system will index and determine what the structure of that mineral is, as well as, importantly, the orientation of that mineral. So it enables measurements of orientation relationships down to the sub-degree accuracy. So just as a refresher, I'm sure we're all very familiar with pole figures, but if we were looking at, say, a cubic mineral in an upper hemisphere projection of a pole figure, we would expect to see three symmetrically equivalent poles to planes for the 010, the 100, and the 001, right? And so pole figures become a very simple and effective way of communicating this information, and that's also where we tend to look for patterns. So let's take this and apply it to granite. This is a high silica granite. Quartz was the first crystallizing phase, and it ended up developing quartz glomerular crysts. And if we do an EBSD map, this is just a color-coded orientation map. Now, our eyes don't pick up on any really useful patterns in a map like this, but we can query this data for certain grain boundaries that have these low energy orientation relationships. And when we do that, we can take this kind of idealized view of the different ways in which these quartz crystals can come together. They can meet on Raman planes, prism planes. They can also meet on the S or X planes, some of the smaller, less frequent for them to meet on these planes. But then they can either meet in parallel orientations with regard to their c-axes. The S-rho twin is, I believe, about 27 degrees apart. Or we could look at orientations, for example, meeting on the Raman planes, but at 90 degrees, or the prism at 90. Now, using the colors that I've put on this example here with the quartz, we can then color code all the quartz grain boundaries that align with one of these orientation relationships. And what's now very immediate looking at this EBSD data is that the majority of grain boundaries that make up these glomerocrysts or these crystal clusters are one of these low energy orientation relationships, which is telling us they have an impact, that low energy configuration has an impact in how these clusters form. We can look at it from a more kind of statistical perspective here, focusing here just on the ROM 90 and the PRISM 90. So the EBSD data will not tell us whether or not we're meeting on the ROM plane or the PRISM plane, but it will tell us the orientation relationship between the two crystals. So if both of these are at 90 degrees to each other, on the bottom, this is a histogram showing the uncorrelated. So if you take all of the orientations in that map I showed you, and you just took two grains and put them beside each other, what's the likelihood that they have a misorientation angle between them? And if we compare that to the grains that actually do share boundaries, so the actual neighboring grains, we can see that the correlated, or the ones that do share boundaries, are very much non-random in the sense of there's a high frequency of grains that meet at 90 degrees. Now, one thing that's missing from this data is we're not seeing anything to do with the parallel grains here, because as EBSD, or how the technique works, two parallel grains that meet together will be imaged or will be analyzed and indexed as a single grain. But we can get around that a little bit. If we collect cathode luminescent images, we can identify through the kind of tree ring or the oscillatory growth patterns of these quartz grains where we have two grains that came together and now they're parallel versus grains that might have grown into a more irregular shape, clustered-like shape. And when we take that sort of approach, we get a bit more information. So what we're looking at here, again, looking at these different orientation relationships. To spell out this acronym in full, it's quartz coincident site lattice orientation relationships. It's another way of just saying the low energy orientation relationships. And if we look at statistically the number of crystal pairs that are within 10 degrees of one of these orientation relationships, we can see both with parallel, with the 90 degrees, and the estero twins, those are highest as we move down from 20 down to 10 degrees. And then the frequency of that drops off as we get to higher energy. And now this might be telling us something about how these quartz grains came together, because the driving force for crystals that are close to each other, maybe they're meeting on their ROM faces, but they're meeting at, say, 45 degrees in terms of their c-axes. That's not a low energy orientation relationship, but if through stochastic processes, they're able to be moved and realigned into a low energy relationship, then the grain boundary energy of that segment is going to drop. Now, an interesting feature here is that grain boundary energy it drops off to a max or to a minimum when they become parallel with each other, or when they become into the lowest energy permissible relationship on those two planes. And the driving force that might actually cause rotation of these crystals drops off as we get closer and closer to our low energy relationship. And that might explain why we still see quite a lot of crystals, a high frequency of crystals, that aren't actually that close, or within 20 degrees, 10 to 20 degrees of these low energy relationships. And that's still occurring at a far more likely or a higher frequency than what random interactions would predict. Now, another thing we can look at with this sintering, if we think back to those two gold particles coming together, immediately after they touched, they tried to maximize the area of that grain boundary that was low energy. And they do that actually by reorganizing or reshaping some of the higher energy part of its grain structure or grain boundary, which is the portion of those, in that case of the gold, the portion of those gold nanoparticles that wasn't touching along that grain contact. Now, if we look at quartz, we can again turn to cathode luminescence, and we can see that we have this nice oscillatory zoning highlighted in the white dashed lines here of quartz grains. In individual quartz grains, they have their own kind of cores that grow outward. Now, if we look at the oscillatory zonation near or at the contact between these quartz grains, we can see that in every case where we have this low energy configuration, there is what I would call a rounding event. So we get this change in the overgrowth microstructure, and it typically ends up truncating what was previously oscillatory growth zoning, and then you get new oscillatory growth zoning overgrowing that. And so that is likely a record of this maximization of that low energy contact at the expense of that higher energy portion of those quartz grains that was just in contact with magma. So we see these records in these igneous and these in these igneous rocks. Now, the implication of this, if we look at this particular sample I looked at, happens to be a historical and a high-producing tin mine, so it's a cassiterite ore deposit. And if we look at the distribution of the mineral incompatible elements, things like tin, copper, and tungsten, that increases in towards a more central horizon. Similarly, if we look at the quartz grain size, that slightly increases in towards the center horizon. And what's really interesting is that the frequency of these low energy orientation relationships of our quartz clusters greatly increases in towards the center of our body. So this is a really nice example of using microstructure to understand the crystallization history of in this case, a high silica granite. So we must have had random grain interactions, quartz crystallizing, and the portion, the center of this body had more time both for the quartz grains to grow, but also had more opportunity for interaction to occur. So one way of interpreting that is perhaps you had dynamic motion, you had convection during crystallization, and it was centripetal crystallization from the margins inward, which would explain this elevation of these mineral incompatible elements like tin. Okay, so that's an example from the igneous side of how grain boundary energy minimization imparts this kind of structure onto the texture or the clustering of minerals. And now we can look at those same principles and think about it more from a metamorphic perspective. So one of the main differences with a metamorphic rock is that we don't have a magma. We don't have this free fluid or magma liquid phase in which our minerals are going to float around and interact with each other. In many metamorphic reactions, it's solid state. We might have some fluid present, we likely do, right at grain boundaries, but this is largely solid state reactions. And so from that perspective, we might want to look at our grain boundaries in terms of the surface topography of interaction potential. So what I'm showing here is chlorite and tourmaline schist from Greenland. And different chlorite grains will have different orientations. And we can look at those orientations and we could look at what, for example, the basal cleavage of those orientations, what the surface interaction, I'm in the kind of gray circles here, we're looking at that, the topology of, or the topography of the van der Waals forces or interactions on that surface. And then we could look at the same thing, for example, with tourmaline. And there's going to be some configurations where this tourmaline is going to be in a lower energy orientation relationship with the chlorite than other configurations of that tourmaline might be. And now when we think about this from a nucleation perspective, that will lower the free energy, or that will lower the grain boundary energy at that contact of that new nuclei forming, which will actually make it easier for that nucleation event to be successful or to occur. And we can think about this from a kind of critical nucleation theory perspective, where on one hand, we have homogeneous nucleation. What might happen in initial stages in a magmatic setting, perhaps. And homogeneous nucleation is best defined on a scale. So at a very, very nanoscale, there's probably impurities or polymers that nucleation is being assisted by, right? In which case it would be heterogeneous nucleation. But on the scale of a magma chamber, if we are nucleating phases that don't have any surface interaction with other previously formed crystalline material, then we could say that's homogeneous. And we compare that to something like heterogeneous nucleation, where maybe we have phases that are nucleating and forming, but we have pre-existing surfaces or substrates. Now that would be very applicable in a metamorphic rock where we have largely crystalline solid state reactions. Now, as a subset of heterogeneous nucleation, we can think of it in terms of epitaxy, where epitaxy is heterogeneous nucleation, but we're inheriting an orientation relationship for the new mineral forming, the child phase or the daughter phase, with respect to that pre-existing substrate. So in the previous example, that could be the tourmaline is going to inherit in its orientation with respect to the chlorite that was already in the rock. Now, epitaxy itself is a very large spectrum from very coherent interaction. So it could be, for example, two very self-similar cubic minerals that can nucleate with a very similar atomic structure across that grain boundary. That would be said to be a very coherent grain boundary. Whereas incoherent grain boundaries might still impart an orientation relationship, or the daughter phase might still inherit an orientation from the parental substrate, but there is less of a kind of atom by atom alignment or lattice alignment between those phases. And when we think about it from an energy perspective, the highest energy pathway here would be homogeneous. So there's this positive energy that is needed to go in to overcome this initial surface bound or surface energy of creating a new nuclei, right? And eventually we get to a critical radius or a size where we now are making enough of our more stable new phase that free energy of making the new phase overcomes or overwhelms that as the kind of deleterious energy of making that new grain boundary. So homogeneous nucleation has this large barrier energy, right? And the actual magnitude of that in kilojoules per mole ranges from approximately 10 kilojoules per mole for a mineral like quartz, up to as much as 500 kilojoules per mole for quarterite, where it's been looked at the devitrification of a quarterite glass. So that's a very large energy penalty. Heterogeneous nucleation, that reduces that energy penalty because there's a substrate that we nucleate on, and it reduces the amount of surface area that actually has to form for that nuclei. Whereas epitaxy, this actually reduces that free energy or that barrier energy to nucleation even greater. But again, it's a scale from incoherent all the way down to coherent, being very, very low barrier energy. So with this in mind, we might expect that metamorphic rocks that are slowly progressing through their reactions are always going to develop epitaxy, or nucleation will always occur in an epitaxial manner, right? And if that's the case, we should be able to turn to EBSD and find the evidence for that. So I'm going to show a couple examples. My group's been working on this for a couple of years now, and we're up to approximately 20 mineral pairs where we've investigated the record or the lack of record of this epitaxy or this epitaxial relationship. What we focused on is these recurring phase boundaries. So mineral pairs where visually, looking in the microscope, we can see, for example, if we look at frame D, many of the tourmaline, or in many cases, all the tourmaline we might observe in these quartz biotite chloride tourmaline schists, all the tourmaline are in contact with at least one biotite or at least one chlorite. So we'd look at that grain boundary. Or we could look at an example like chloratort and storlite in the interaction between them. And when we look at these recurring grain boundaries, we have to ask ourselves, is this recurrence or this common observation a product of epitaxy and the reduction of free energy of nucleation? Or is this because diffusion is limited and this is just where the components for our new nucleating phases lie? And the answer comes from looking at orientation relationships. So I'm going to start with a couple simple examples that get slightly more complex, and then I'm going to sum this portion up, and then I'm going to move into some applications of these theories. So first, let's look at one that has been known for a long time. Storlite and kyanite often form integrals. Storlite can be thought of as a fourth aluminum silicate. You just have to add magnesium. And storlite and kyanite have very similar crystal structures. Now, if we look at an integral of storlite and kyanite, what I'm showing here is a XRF phase map, and in dashed line, that's the area I scanned with EBSD. And then down in the bottom of these pole figures, what I'm going to do for all these kind of subsequent slides here is I'm going to rotate all of the parental phases into a common reference orientation. Now I'm going to apply the exact same rotation on a pair by pair basis for all the adjacent daughter crystals. So in this case, there's a single storlite, single kyanite. So we're just going to rotate our storlite and the kyanite will have that same rotation. But in subsequent examples, we might look at hundreds of these grains and then look for patterns in those post-rotation orientation relationships. So looking at storylite here, we can see, for example, the poles to the 001 plane here of kyanite overlaps with the pole to the 001 of storylite, as does the pole to the A, so the 100 overlaps with the poles to the 010 of storylite, right? So we have this very clear orientation relationship. And the best way of defining this is with this plane direction notation. So we should have at least one set of planes between the parent and the daughter that are parallel. In this case, we can look at the 010 of the storylite, and we can look at the 100 of the kyanite. And then we should also have a set of directions that are parallel. In this case, we could look at the C axes of storylite and the C axes of kyanite, right? And so that would be our definition of that relationship. Once we have that relationship, we can then visualize what the grain boundary or what the interaction of these grain boundaries might look like using a program like Crystal Maker, or there's a few different crystal visualization programs that work very well with this. So we take the crystals, storylite and kyanite, we cut them along these planes that we're observing that are parallel with each other in the EBSD data, and then we orientate those planes so that the directions that are parallel with each other remain parallel. And we do that with storylite and chlorite, with storylite and kyanite. We can see, oh yeah, there's quite a lot of, or there's very little mismatch or coincidence between the spacing of, for example, aluminum to aluminum, or silica to silica in the storylite and the kyanite. So there could be a lot of bond interaction across that boundary, and that could result in a very low energy orientation relationship. That's a simple one. Let's move into something that's a little bit more complex. Here we've got a single Andalusite grain, and it's kind of fringed by this retrograde muscovite. And if we take our Andalusite, we rotate it into our common reference frame, and we apply that same rotation to all the neighboring muscovite, what we can see is that our 010 plane of our Andalusite aligns very nicely with this maxima in the 010 planes of muscovite. So pole figures like this, what I'm showing, are contoured, and they're contoured pole figures with respect to what is called the MUD, or the multiple of uniform distribution. So a multiple of uniform distribution of 1 means that it's random. If you have a multiple of uniform distribution that's increasing in number, it's increasingly non-random. So these are fairly nice maximas showing this orientation coincidence of our B plane and our B plane. And then we can see orientation coincidence of our C axis and our C axis between our Andalusite and our muscovite. And again, we can visualize what that might look like, and we can see, well, there's only 4% mismatch over about a 20 angstrom spacing when we align our two minerals this way. And we look at the alignment here of the, for example, aluminum octahedral layer in muscovite compared to that in the spacing of aluminum in the Andalusite. Okay, I'm going to show 2 more examples of this, and then I'll sum this section up. So the next example is looking at a slightly more, one that'd be even more difficult for us to visualize, because we're going to look now at multiple chloritoid. And muscovite is overgrowing chloritoid. So now we're going to take a whole range of chloritoid, approximately 30 crystals. We're going to rotate them all into the same chloritoid reference plane. This is the chloritoid reference plane on the left-hand side of our pole figures. And then we apply the same rotation to all the adjacent muscovite grains. And when we do that, we see a very nice pattern here with a rather high multiple of uniform distribution. So again, the B plane of muscovite overlaps that of the B plane of chloritoid, and the C direction, or the C axis of muscovite, is parallel to that of the C axis of chloritoid. We can align what those crystals look like, and we can explore in terms of the spacing of the different elements or the atoms in here, why that similarity, what sort of interaction we might be getting across that boundary. The final one I want to show is just to illustrate that this doesn't just apply to metapelites that are regionally metamorphosed or contact metamorphosed. Here we're looking at a decompressed amphicite-bearing blue schist from Cerros Grace. And at peak conditions, we would have had garnet and amphicite, glaucophane. And during decompression, as we get down to about 1 gigapascal pressure, actinolite, a small overgrowth of actinolite started to form. Now that actinolite preferentially is growing along grain boundaries of glaucophane and grain boundaries of amphicite. And what we can see in both of these examples here, so look at the top first, glaucophane on the left, this is post-rotation, and actinolite on the right, we see a very nice coincidence of all the orientations of actinolite with respect to that of the other amphibole, the glaucophane. Now we can see something similar with the amphicite, so the pyroxene amphicite with respect to the actinolite. And so we see that actinolite is growing in multiple sites, multiple parts and grain boundaries within this mineral, or within this rock, but in all cases here, it's inheriting its orientation from that of the parental phases, the glaucophane and the amphicite. So with this, I think we have enough to start exploring what the commonalities of all these different relationships are. So I'm going to put up 8 here on this slide. We're just looking at this kind of crystal visualization of these orientation relationships. And just to remind you, these are all shown, or the orientations I'm showing you here were all the patterns that we're pulling out of the EBSD, the pole figure analysis. So the plane to the plane parallelism, that's the cuts that we're viewing here. And then the direction to the direction parallelism, that's how we're positioning or orientating these. And some of the kind of commonalities of this, collectively, for lack of a better word, I'd say could be defined by 3 rules and 1 suggestion. So the first rule is that the daughter phase, so the new phase nucleating, is going to nucleate on compositionally self-similar phases. For 2 reasons. 1 is because then if you do that, you have a higher potential of covalent and ionic interactions between those 2 minerals along that grain boundary. But another important aspect here is that the parental phase is likely going to be the source of the least mobile cation. So whether that be aluminum, iron, or titanium, these are the cations that aren't necessarily traveling fast or far throughout our rock. And so we're going to nucleate a daughter phase in an environment where that is more abundant. The second rule is that the nucleation the nucleation contact plane for the daughter phase, so what plane that daughter is actually going to nucleate on, is always going to be the one that maximizes its structural inheritance on the scale of a supercell. And so to illustrate that, let's look at muscovite, tourmaline, and actinolite. So all of these have a layered structure to them, to their crystal structure, and they are the observed epitaxy relationship is always one that allows the plane of epitaxy to be perpendicular to that layering. So take example muscovite. If we looked at the spacing of those octahedral aluminum in that octahedral plane, and we compared it to the aluminum along, for example, the B face of andalusite, there's a lot of similarity. But if you nucleated muscovite in that orientation, all you would do would be reducing the energy of making a single octahedral plane, right? And that doesn't make a muscovite structure or the superstructure of muscovite. Whereas if you nucleate in a way where you're inheriting that layering, that kind of scaffolding of your supercell structure, then you are nucleate, or you're reducing your free energy or that grain boundary energy on the scale you need to actually overcome that critical radii of nucleation, right? These nuclei, these are forming on nanometers to even tens or hundreds of nanometer scale before they're successful. And that is far beyond the unit cell scale, and you're looking at supercell structures. The third rule is that when it's permissible by the similarity of the 2 crystal structures, you're always going to get what's called either syntaxy or sometimes referred to as topitaxy, which is the 3D inheritance of orientation. So whereas epitaxy, most broadly defined, is the inheritance of orientation across a 2D plane, if that surface structure, that mineral interface that you're nucleating on, has some steps to it, then you could also inherit not just on a 2D plane, but also in 3 dimensions. And in all cases where that's permissible, because of the similarities of the parent and the daughter product, take, for example, actinolite and glaucophane, or amphicite and actinolite, then that's what we see. We see this inheritance of orientation in more than one direction. And finally, the suggestion is that the contact plane for nucleation for the parent and the daughter phases, at least in all the examples we've seen, is always a low index phase. And this probably isn't something that should surprise us for two reasons. One is that low index phases are statistically quite highly represented or overrepresented in most natural metamorphic rocks. That's because they tend to be the stable phases, the idiomorphic phases, cleavage planes, or twin planes. And the second reason is by design how we're describing our unit cells, we're setting it up in a way that our low index phases tends to be the most stable crystal planes. Okay, so that's a bit of a whirlwind tour through the work that my group has done in terms of identifying epitaxy. Now let's take a bit of a shift and say, what are the applications of these theories or these ideas? And to do that, my group started looking at some experimentation with salt systems. So on one hand, we had built up this kind of observation base of epitaxy being very common in metamorphic rocks. So an example like diopside and hornblende, where the orientation of that hornblende is inherited from that diopside. Now, there's other examples in nature where we have this very non-random orientation relationship. Here we have a quartz vein. It's called a syntaxial quartz vein in a green schist rock. And we can see that we've got this structure or texture to the orientation of our quartz grains here. Now, on the other hand, in a lot of igneous rocks, people have studied the orientation relationships. For example, on the top here, we're looking at a chromatite rock. So this is chromite and an ultramafic rock. And the orientations of those chromite crystals with respect to one another, in all the cases that have studied this, appear to be completely random. So why on one hand we have complete random nucleation occurring, and then in other settings we tend to very much bias towards epitaxy. And somewhere in between, we have examples like this really nice one from NIMS 2019, which looked at chromite inclusions in diamond. And what they found is that the chromite inclusions always appeared to have at least one plane of the chromite parallel with one plane of the diamond, but there was no systematic control of a rotation about that plane. So these are meeting plane to plane, but there's no orientation control. So we wouldn't really call that epitaxy. And their conclusion was that these minerals were coming together on planes like synusis, but there was no control or there's no reason for them to be rotated into a low energy configuration. So it'd be nice to be able to explain all this together with a kind of common set of understanding of why nucleation can be homogeneous, heterogeneous, or epitaxial. And the approach that my group took was, we're not really experimentalists. So we said, what's the simplest experiments we can run? And this was doing halite or salt on mineral surfaces. And so the first approach we took was we took polished thin sections. In this case, this was a granite. We made some saturated or near saturated solutions of halite, and we put our thin sections in the bottom of these beakers. We let that system evaporate over time and saturate and start to crystallize halite. And then we looked at the orientation relationship between all those different halite crystals and the surface that they were landing on. And what we found was there was no real relationship, or there appeared to be a relationship where planes of halite were always aligned with the surface of the thin section, but there was no relationship with the actual orientation of the mineral that was making up that surface. So if we looked at quartz to quartz crystals of different orientation, there was no change in the halite orientations that were lying on top of those. And this puzzled us, and we're not experimentalists, so it took us a long time and many, many experiments until we figure out what was happening. And we started to become more systematic with this, and we took the approach of taking minerals like fluorite that have a very similar unit cell or crystal structure to halite, and we would mount them in epoxy. We would polish them down to as smooth as a plane as we could, and then we would make a warm, near saturated solution of salt, in this case 60 degrees, put droplets of that on our mounted fluorite and the epoxies that surrounds it, let the cell crystallize, and then we'd image those orientation relationships. And when we did this, what we found looking at, for example, halite on fluorite, all the O10, or sorry, the 100, O10, and the 001, these are our cubic faces. We've got, oh, this should say 3. These are our 3 cubic faces of our chloride. One of those faces was always landing so that it was directly on the surface. And if you take the pole to the plane of something landing on the surface, it's going to be right in the middle of your pole figure. And then if we look at the 111 poles to planes, so these are the octahedral faces, we can see there's just this small circle rotation about the center, so about that center there. And the exact same pattern is observed in fluorite, which has a very similar unit cell or structure to halite, as is our control, which is our epoxy. What does this mean? What it means is that halite is falling down on the surface and it's just landing on its idiomorphic faces, like dice landing on a table, right? In some cases, we have a few halite grains that are forming this octahedral shape, in which case we get these 111 right in the center. But in the vast majority of cases here, we're getting cubic halite forms and they're landing right in the center. So that is definitely not epitaxy. If we then look at another salt system, so this is KCl, and it crystallizes as sylvite, another very accessible and simple experiment that non-experimentalists can do. And we crystallize this, again, bringing it near saturation at 60 degrees, putting it on our mount of fluorite with epoxy. We find something very similar, or very different. So on the top half here, or the top example, these are 2 different experiments with the same kind of control conditions. What we found is the orientation of the fluorite, the underpinning substrate, is these red dots here, right? So 3 cubic faces. And the orientation of the majority of our sylvites perfectly align with our fluorite. That's epitaxy. Now, there's a few examples of grains that are still landing right in the center, perhaps much like we're seeing with our halite. So there's epitaxy and there's probably homogeneous nucleation with some raining down of crystals. Now, in the second experiment we ran, similar set of conditions, just trying to replicate here, we don't see very much in terms of this raining down of cubic forms on the surface, but we see a very strong example of epitaxy. And if we compare that with our epoxy, so again, the sylvite, same experiment, crystallizing on the epoxy, on one hand, in one domain here, what we see is a very nice random distribution of these sylvite grains. Now, on the other hand, or in the other example, we see the same pattern as we saw with halite. So if we look at the bottom pattern, that's homogeneous nucleation, cubic or octahedral crystals of sylvite are landing on the surface. Whereas this other example here, this is probably best thought of as heterogeneous nucleation, where we're nucleating on the surface and it's reducing our nucleation energy to form on the surface, but that surface has no crystalline structure, so there's going to be no inheritance of control or no orientation control from that structure. And it took us a little bit of time to figure out why this was the case, and it all came back to a very kind of simple observation, what you would read in a first-year chemistry textbook, which is that the saturation or the supersaturation dynamics of these different salt systems change with respect to the solubility and temperature. So if we look at halite on the bottom here, this is essentially a flat line in terms of the solubility at temperature. There's very little change of halite solubility in water with temperature. And what that means is that if we put our temperature, we start our system near saturated at 60 degrees and let it cool, we're not going to have any saturation occurring system-wide because of that cooling. Whereas we can saturate quite readily by evaporating, right? The problem is that evaporation occurs away from our substrate. It's occurring at the vapor to, or the atmosphere to liquid boundary. And where that evaporation is occurring and the rate at which evaporation is occurring is quicker than the rate at which we're actually able to re-equilibrate the ionic concentration of our sodium and our chlorine in our droplet here, which means that we're saturating along that bubble surface, and then we're raining down on that surface. So that explains what we're seeing in halite. Whereas if we look at what's happening in sylvite and in niter, which I didn't show you the examples of here, here we can saturate our system quite readily by cooling. So if we form our solution at 60 degrees and we put it on our slide and let it cool to room temperature, we're saturating system-wide. And a way of understanding this is that where we saturate system-wide, then the lowest energy nucleation pathway, which in most cases is going to be epitaxy, is going to be expressed, right? And this explains why a lot of metamorphic rocks, which have changes in pressure, temperature, chemical potential that are occurring at a much lower rate than the rate of mass transfer in those rocks. Those allow epitaxy, or that system or that set of conditions allows epitaxy to be expressed. Whereas if we look at what's happening in a lot of igneous rocks, crystals are growing. They're growing at a rate that is actually outpacing the local mass transfer rate of the components in the fluid or the liquid, the magma that's surrounding them. Locally, you end up supersaturating different components. And so in igneous rocks, homogeneous often is a dominant nucleation pathway because we are locally saturating. Whereas in metamorphic rocks, we have this system-wide saturation. So if we want to use that concept to then explain some of these initial observations, we can turn back to one of these chromatite layers. So here's chromite, orthopyroxene, olivine, and clinopyroxene. This is the EBSD phase map. So this is a map where we've done EBSD, we've indexed the phase, and we have the orientation of all these crystals. Looking at, for example, the olivine and the chromite, there is near random distribution of all the different orientations. What that tells you is that the olivine and the chromite, those are saturating somewhere in your system, they're nucleating, and then they are moving and they're falling or they're being mobilized into the position that we see here, like a cumulate, right? Whereas if we look at the relationship between orthopyroxene and clinopyroxene in the same rock, which probably has a similar cooling rate to the cooling rate at which olivine and chromite formed, in the same rock, the saturation is occurring under conditions where we're expressing epitaxies. So the clinopyroxene is the exact same orientation of that as the orthopyroxene. All right, so we can start to get an understanding of these different kinetics of nucleation. Another example here is when we look at a very nanoscale. If we look at tourmaline nucleating on biotite, it's an example I've talked about previously. This is the orientation relationship that is commonly expressed in metamorphic rocks. If we take this to the TEM and we look at the nanoscale, what's happening? On the left-hand side, we have biotite. We can see our basolattice fringe of our biotite. On the right-hand side, we have our tourmaline, or schorl. And in the middle, we have rutile forming. Now, what's important is that this rutile, in all cases here, the rutile, the biotite, and the schorl, or the tourmaline, they're all in epitaxy type relationship with one another. They're all in a similar low energy configuration with each other. So the biotite was there first, the tourmaline started to grow, it inherited its orientation from the biotite, and as the tourmaline continued to grow, it doesn't like titanium, it doesn't take titanium into its crystal structure, and so the titanium from that biotite had nowhere to go, so you start to make these nanoparticles of rutile, and you get these titanium oxide or rutile particles that are again forming epitaxy with the surrounding biotite and the tourmaline. Now, another mineral that is more compatible in our biotite than it is in our tourmaline another element is iron. And what we observe in some of these domains between tourmaline and rutile is actually goethite formation. Now, goethite is not a stable mineral product. If we think about this from an equilibrium perspective, when we have this reaction from biotite adding in boron as a fluid or out of a melt and forming tourmaline, goethite isn't predicted as one of the lowest free energy stable products. However, under very local saturation conditions, that iron has nowhere to go. And the amount of iron, or it doesn't have anywhere to go, it's not able to move out of that grain boundary at a rate that's fast enough to maintain equilibrium. And so we supersaturate locally and we end up developing goethite nanoparticles that are metastable. So we can think about this in a simple ternary system where we have a biotite as our parental phase, and that breaks down in a ternary reaction to rutile, tourmaline, and goethite, thinking about it in terms of titanium, aluminum, and iron being the three potentially least mobile cations during this reaction. So on the nanoscale, even in a rock that is system-wide saturating at a slower rate where we're developing epitaxy, on this very small scale, we still have these supersaturation kinetics that are leading to these metastable products. And this goethite that's forming has no structural inheritance from either the tourmaline or the biotite. So to bring it towards the kind of close and the final applications here, there's a famous quote from one of the godfathers of evolution, which is nothing in biology makes sense except in the light of evolution. Nothing in biology makes sense except in the light of evolution. Well, nothing in the study of microstructure makes sense except in the light of grain boundary energy and how it can be minimized. And one of the examples of how we could use this theory is actually for identifying ultra high pressure terrains. So this was an experimental study that a former postdoc of mine, Relly Goddard, led, where she took quartz, brought it up to coelcite pressures, and then rapidly brought it down to quartz pressures again. And then we took those experiments, cut them, imaged them with eBSD, and we looked at the orientation relationships between the quartz and the coelcite. And what we found is that you end up forming a Japan twin in the quartz that grows. And this is because this is not because, but the Japan twin, so the two orientation relationships for quartz that form, they form on a common B face or B plane of our coelcite. And this crystallographic relationship is a really nice one because it's defined both by an angle between our C-axis, approximately 84 degrees, but importantly, it's also defined by having a common M plane, right? And we can think about this in terms of why our two quartz crystals or quartz orientations might inherit these two orientations. We can look at our coelcite M plane or our coelcite B plane, and it's orthogonal, so it's got two 90-degree orientations to each other that have very similar atomic spacing of the silica. Now, when we look at where we get the same atomic spacing of quartz, well, we get that when we configure it or we position it where we're looking at the M plane of quartz, either aligned with the C-axis in one direction, so approximately 84 degrees up to the top right, or the other direction rotated 84 degrees down to the bottom right here. In those two configurations, we're getting these 90-degree orientations of our silica tetrahedra at approximately the same spacing as what would have been on that coelcite B plane. So with that kind of signature, we can then go to areas where UHP metamorphism and the presence of coelcite has long been suspected on the basis of other petrological barometers or indicators like silica in phengite barometry or on the basis of garnet compositions. Here's an example from the St. Cyr eclogite in Yukon. It has been suspected that it got to coelcite conditions, but coelcite has never been found. If we then image the orientation relationships of all the quartz, we can find that you have this two common orientations where we have shared grain boundaries between two quartz orientations, and these are 84 degrees from each other in their C-axes, and importantly, they align with a common M plane. And in the case of this example, there's actually 3 of these different orientation relationships found in this rock. We can compare that against statistically how likely it is that these orientation relationships randomly occur if you have 1,000 quartz grains in a rock. And for three of them to occur, we have a probability value far less than 0.01. So it's very unlikely that randomly occurred. And instead, this is a nice signature that the quartz nucleated off of a former coelcite, which is now gone, right? So it's that ghost signature of coelcite. Another application of this epitaxy theory or this grain boundary minimization theory is we can look at a common feature like chalcopyrite disease or these sphalerite starlets. In this example on the right here, we have this chalcopyrite as a host, and these starlets of salarite forming. And there's different interpretations as to why that occurs. Could it be cold precipitation, partial melting? It could be exsolution. Well, we can rule out some of those potential interpretations when we look at the orientation relationships. So in the case of the chalcopyrite, it has a twin plane that runs right through it, which means in the pole figures for the chalcopyrite, we're going to have two different orientations. Those are the two different orientations on either side of that twin plane. Now, if we look at that salarite starlet that forms on that twin plane, we find both of those orientations are coincidentally expressed, right? So that salarite starlet, it nucleated after that twin plane was already there. So it gives us that relative timing, and it rules out, for example, cold precipitation, whereas instead we must have developed a twin plane, and then through exsolution or diffusion or some other process, we end up nucleating that salarite. So there's a lot of application for this beyond what I'm showing here. And the final one is, this is an idea that I haven't really had time to explore very much, but I'm saying it here in case anyone in the audience wants to pick it up and talk to me about it. If we look at, for example, the CPO inheritance, so the crystallographic preferred orientation of the mantle, experimentally, we can reproduce some of the upper mantle textures, but we can't reproduce easily or readily the mantle textures once we start to transition outside of the olivine stability field. So as an example of what's happening and why this is important, for example, in the upper mantle, if you take a single crystal of olivine and then you nucleate antigerite on it, that orientation of antigerite, if it inherits its orientation from olivine, antigerite has much higher shear wave splitting. So the different axes of antigerite have different shear wave velocities, whereas olivine is more isotropic in that sense. And so this inheritance of a CPO from olivine leads to an important structure to your shear wave velocities. Now, we could take our theory of epitaxy and expand it deeper into the mantle. So if, for example, we could look at olivine to ringwoodite transition, and with that transition, we could look at what the lowest free energy configuration of that grain boundary might be, applying the 3 rules and 1 suggestion of epitaxy. And by doing that, we would get olivine A plane parallel to the 1-1-1 plane, so that octahedral plane of the ringwoodite. Now, if that were to exist, if that is what happens in nature, that's important because this is actually the fast direction of ringwoodite aligned with the slow S-wave direction of olivine, which means that you're going to get shear wave splitting as you transition from olivine to ringwoodite. So again, this is just applying the theory, but this is the sort of direction we can take this work now. So I'm going to just summarize this all now by saying that the grain boundaries, mineral surfaces, and the systematic or the periodic arrangement of atoms at their surface, that imparts this electrostatic potential that has a kind of repeating topographic periodicity to it. And that influences, the influence of that on grain boundaries is wide-ranging, all the way from glomerulocrystal formation in magma dynamics to the kinetics of nucleation. In the sense of metamorphic rocks, what we are finding is that epitaxy is very much the norm rather than the exception. And that shouldn't be a surprise because it is the lowest energy expression or nucleation pathway. Now, why some rocks express epitaxy and other rocks don't, that likely depends on the saturation kinetics. So when the forcing rate is faster than the rate of mass transfer, then you can have you have more saturation, you have more energy available for homogeneous nucleation and higher energy pathways. Whereas when the forcing rate is slower than mass transfer, like in many metamorphic rocks, then you're going to express epitaxy. With that, I'll just thank some contributors and some funders, and I'm open to any questions you have.
All right, it's got to get back online here. That's excellent, Brendan. Thank you very much for that. I noticed we had quite a few participants, right? So I think it was amazing that we were all able to get together and enjoy this presentation. Right? I saw some early versions of this. I can't remember where. Maybe it's Sudbury or something. And it was so. This is a much more evolved, bunch of ideas here. Right? So well done. Right?
Thank you.
I have a quick question on the hardware because I'm sort of a hardware guy. What are you guys using for your EBSD